Hi and Assalamualaikum. My name is Muhammad Faris Firdaus bin Saharom. My number matric is CE210211. So this is my group members, Muhammad Asyraf bin Muhammad Safie, number matric AE200100, and Muhammad Hazlisyam bin Hanafi, number matrix AE190032. We are from group 6. Okay, today we are going to present ECAD project. So for introduction, we use third order bandpass filter that design improve the device performance characteristics such as enhanced power efficiency and switching capabilities due to the properties of DG MOSFET technology. Simulation analysis of the proposed filter model has been performed. The bandpass filter model has been designed for lower and upper cut-off frequency of 1.5 kHz and 15 kHz respectively. So the frequency value are given for each group. The third order bandpass filter has been modeled to have butterworth characteristic, thus having a maximally flat pass band response. The value for gain third order is negative 60 dB over decade. Active bandpass filter are frequency selective filter that are used in electrical system to separate a signal at a certain frequency or a range of signals that are within a specific frequency band. The capacity of a band pass filter to pass frequency relatively unattenuated over a given range or dispersion of frequencies. It is referred to as the pass band. The active pass filter is separated into two types, which is low pass and high pass filter. The well-known low pass to band pass frequency transformation is often utilized in the design of band pass filter when applied to a low pass prototype filter transfer function. So here is a diagram for high pass filter to amplification to low pass filter and to band pass filter. Okay. So for the discussion and elaboration on the importance of active filter in electronic system and relate it to the current technology trend, the principal characteristic of a bandpass filter is ability to pass frequencies relatively attenuated over a specific band and spread of frequencies called the pass band. A simple active bandpass filter can be easily made by cascading together a single low pass filter with a single high pass filter as shown. This band or range of frequencies is set between two cutoff or corner frequency points labeled the lower frequency FL and the higher frequency FH, while attenuating any signal outside of these 2 points. However, the active bandpass filter is slightly different in that it is a frequency selective filter circuit used in electronic system to separate a signal at one particular frequency or a range of signals that lie within a certain band of frequencies from signals at all other frequencies. While the above passive tune filter circuit will work as a bandpass filter, the pass band bandwidth can be quite wide, and this may be a problem if we want to isolate a small band of frequencies. Active bandpass filter can also be made using inverting operational amplifiers. So by rearrange the positions of the resistor and capacitor within the filter, we can produce a much better filter circuit. For an active bandpass filter, the lower cut-off -3 dB point given by FC1 or FL, while the upper cut-off -3 dB point is given by FC2 or FH. So So here is the diagram shown for FLFH. Nowadays, the use of filter in modern technology is quickly increasing. For example, automobile, entertainment system, broadcasting, and so on. According to the Tech FAQ, a Butterworth filter is a signal processing filter with an extraordinary flat frequency response. It is extensively employed in both digital and analog audio crossover filters in both residential and business setting. For example, audio crossover are utilized as electronic filter in audio systems. It is difficult for speaker driver in these systems to appropriately cover the whole audio spectrum by utilizing suitable volume and distortion control. As a result, the entering audio signal must be filtered into various frequencies for which the system is built. Lastly, active filters are used in biomedical equipment to connect psychological sensors to diagnostic tools and data logging. For example, an electrocardiogram (ECG) utilizes a Chebyshev filter to remove noise from ECG data. ECG are used to access the electrical activity of the heart as well as the status of the cardiac system. Time variation voltage produced by myocardium during the cardiac cycle are also recorded or shown by ECG. Chebyshev filters are commonly employed because they have higher pass band ripple and stop band ripple. When compared to the Butterworth filter, the Chebyshev filter has a sharper roll-off and can lower the error between idealized and real filter characteristics.
Okay, now we move for theory. To finish the task, we must use the OP-AMP to construct a three-order bandpass filter. A bandpass filter, or any filter for that matter, is defined by its capacity to pass frequency over a design band or range of frequency known as passband comparatively embellished. We must combine a high-pass filter and low-pass filter to create a bandpass filter circuit. The high-pass filter circuit only allows signal above the chosen cutoff point. Therefore, removing all low-frequency signal from the waveform. We create the third-order bandpass filter by combining first-order and second-order filter. So, this is a specification that gives to my group. For mid gain, the value is 75, and for low cutoff and high cutoff, 1.5K and 15K. Other frequency in this range will be filtered out using three-order active bandpass filter, which only accept the inner frequency range between 1.5 and 50 kHz. Firstly, we need to calculate the resistor value for high and low pass filter. So this is a manual calculation. Firstly, we need to calculate high pass filter and low pass filter. For high pass filter, we get value for resistor 106.1, and for low pass filter 1061.03. Next, we need to determine RF and RA. If RA 720 ohm, we get RF 2.3977 kilo ohm. Next, for total gain, we get 75.01, and for converting the gain for bandpass, we get 37.5 dB. For bandwidth, we need to get 13.5 kilohertz, and for quality factor, we get 0.351.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Asyraf bin Muhammad Safie. My metric number AE200100. So for my part, this is the circuit diagram. So for figure 4.1, this is the circuit diagram using Proteus simulation software, and we from this design we convert it into actual hardware connection. So this is what it looks when we connect all of the components. And for table 4.1, this is the list of components that we used to construct this third order bandpass filter. So for number 5, this is the result from the simulation done on the circuit using the simulation software. So from the circuit that we create using Proteus, we obtain the frequency response graph, and this is what it looks like. And this is the bit gain from the simulation is 37.5 dB. So to convert to unitless, we got around 75 unitless, and this is close to the theoretical and our filter specification. And to get the FL and FH, we must minus with 3 dB. So minus 3 dB, we get 34.5 dB, and for FL is 1.52 kHz and FH is 15.2 kHz. So the difference is around 200 Hz. And for number 6, the analysis and discussion on the simulation result and comparison with the theory. So after we done the simulation, we also do the experimental testing. So for experimental testing, we vary the frequency. So you can see at the table here, we this is the value for V in and V out for each frequency, and we calculate the gain and we compare it side by side, so we can see the difference between simulation and experimental result. Okay, so this is the proof that we test the component at the lab, and this is our first try. We got this frequency response, and this is for when the FL is 1.5k. So the frequency is 1.5 kilohertz, and we get the V in is 1.02 volt, and the V output is around 35.6 volt. Okay, so from the table, we plot the graph using Microsoft Excel, and this is what it looks like. The gain versus frequency, and the mid gain is 34.5 dB, and to get the FL and FH, we must minus 3 dB. So for the experimental result, the FL we get is 1.8 kilohertz and FH is 18 kilohertz. So this is the comparison between theoretical result and simulation result. So for mid gain, the theoretical is 37.5 and the simulation is 37.5, which is the percentage error is 0% because it is the same. And for FL at 34.5 dB is for theoretical is 1.5 kilohertz, while simulation is 1.52 kilohertz. The percentage error is 1.33%, and for FH, the theoretical is 15 kilohertz and simulation is 15.2 kilohertz, and the percentage error is same as FL, 1.33%. So this is the comparison for theoretical and experimental result. For mid gain, the theoretical is 37.5, but from the experimental we get 34.5 dB, which is the percentage error is 8%. And for FL is for the experimental we get 1.8 kilohertz, so it have around 300 hertz difference. So the percentage error is 20%, and for FH is the theoretical 15 kilohertz while experimental is 18 kilohertz, and the percentage error is 20%. And this is the comparison between simulation result and experimental result. So for mean gain, simulation is 37.5, experimental is 34.5. For FL, simulation is 1.52 kilohertz, experimental is 1.8 kilohertz. And lastly for FH, simulation 15.2 kilohertz and 18 experimental result is 18 kilohertz. So this is how we want to find the gain at low and high cutoff frequency. So 37.5 dB minus 3 dB, we get 34.5 dB. And for percentage error, is the formula for percentage error is original value minus observed value divide by original value and multiply with 100%. So that's all from me. Thank you.
Lastly, for conclusion, the assignment requires us to develop and simulate a 3-order bandpass filter using an OP-AMP based on experiment. We design the circuit using Proteus software, calculate the circuit manually, and then simulate the hardware prototype. We compare the result of our software design and hardware prototype and found that there are slight difference. Possible cause of the different result values include human error when taking value and loosely connected component. From the assignment, we conclude that the bandpass filter is the filter that we should use if necessary for incoming electric waves that are placed in certain frequency range to pass through and block all other. So, that's all from my group. Thank you.